So for question 26, we want to find the limit as x approaches infinity for each of the following. We're supposed to explain our thinking and not we're supposed to really use a graphing calculator. So here on this first one, so as x is getting really large, we have this 1,000 is going to stay the same. This 1 isn't really changing. But if we think about it, if x was like 1 million, 1 billion, like a trillion, this whole fraction is going to decrease, and it's going to keep decreasing because x is in that denominator. So we're going to keep dividing by larger and larger numbers. So as we do that, y is going to decrease down to 0. Now our next question, b, it's pretty similar. We're looking at 5 minus 1 over x. So as x is getting really large, this part is going to keep on decreasing. So 1 divided by larger and larger and larger and larger numbers, that's going to eventually become pretty close to 0. So we're going to have y approaching the value of 5. Because that's going to go away. All we're left with is that 5. 5 is not really being impacted by any values of x. Now, a little bit trickier. As x approaches infinity, we have an x squared here. We also have an x squared on top, or we have an x on top. So I guess the way that I'm going to think about it is that as x gets larger and larger and larger and larger, eventually our value is going to approach x over x squared. Just because for really large values of x, this minus 4 and this plus 1 are going to become essentially just negligible. They're not going to be impactful in our value as much as x gets larger and larger and larger until the point that they're just completely unimpactful. Now here, this, what we have here, that's the same as writing 1 over x. We know that as x gets really large here, this whole thing is going to go to 0. So we know that y is going to approach 0. Now on 27, we have a pretty similar question. What is the limit as x approaches infinity of x minus a over x minus b, where a and b are real numbers? We need to explain our thinking without the use of a graphing calculator. So kind of similar to what I did here. As x gets large, our function y will become more like x over x. Because as x gets really big, subtracting a and subtracting b is going to start mattering less and less. Like if we had 1,000 minus a over 1,000 minus b, or 1,000,000 or 1,000,000,000, those a and b, those aren't changing. They're going to be staying the exact same value. So a and b are not going to be super impactful. So we know that y is going to behave more like x over x, which we know is equal to 1. So therefore, y is going to approach 1 as x goes on to infinity. Question 28, we're looking at a rock tossed into a circular pond, creating a circular area, ripple with area a equals f of r square meters. It has radius r meters. The radius is a function of t, and time t seconds after the rock hits the water. So what is the meaning of f of h of t? So I guess let's just kind of unpack this. We have f on the outside. F here, that's the area of the ripple. And then our independent variable that's going in at the very beginning is the seconds after the rock hits the water. So I'm just going to write seconds after impact. So if we notice, then what we essentially have here is that we're inputting seconds after impact, which is giving us the radius, which is going into F, which gives us the area. So we're putting in T and we're getting out F. So we have the area of the ripple as a function of the time since the impact. Next, the question we're saying let f of x be g of h of x. So that means that we're putting in h of x to g of x. Now for each part listed below, we're going to find two sets of possible formulas for h of x and g of x, assuming g of x isn't just x and h of x is not just x. So first, what I'm going to look at here, we can come up with two different ways to write this. So I guess first, let's just say what if h of x is this? So that would look like h1 of x is e, let me write that, is e2x. And now that's being plugged in here. So in our g of x is going to just replace that whole thing. So g of x would be 3x plus 1. Now we can check that because if we kind of write it out again, g of h of x, g1 of h1 of x, would look like 3 with e to the 2x instead of x plus 1. And this is the same as what we're given. So we're good on that. Now, next, we want to look at kind of a different, what if we wrote this a different way? What I'm going to do here is say, okay, well, let's just take the whole thing as h of x. Say let h2 of x be 3e to the 2x. Now again, like we did earlier, because h of x is all right here, I'm going to put in, to say that's x and g2 of x. So that g2 of x will be x plus 1. Now to check, we have g2 of h2 of x, which looks like 3e to 2x plus 1, which is the same, again, as what we started with. So we're good on that. Now here we have 2 times x plus 1 to the 5th. So again, there's a couple different ways of doing this. So first I'm going to say, what if h of x is just x plus 1? X plus 1, which means that in our g1 of x, this whole thing is going to be replaced with just x. So g1 of x is going to look like 2x, and this whole thing is being raised to the 5th. So that is what's going to go there. Now, let's pretend we have, I guess, just to check it, g1 of x, g1 of h1 of x is going to look like 2 times x plus 1 raised to the 5th, which is indeed what we started with. So we're good on that. Now, there we go. What if we wanted to go a different way? Maybe we wanted to say, okay, well, let's put this whole thing as h2 of x. So h2 of x, I'm just going to say is x plus 1 raised to the 5th power. That would make g of x, replacing this whole thing with x, 2x. Now again, just to check, g1, or g2, sorry, of h2 of x is going to be 2 times, we have a x plus 1 to the 5th. And now this, again, same as what we started with. So we're good. Moving on to question 30, we have let f of g of x equals 3 natural log of 2x minus 1, and g of f of x is equal to natural log of 6x minus 2. We want to find possible formulas for f and g. So I guess first I'm going to kind of focus on this g portion, g of f of x here. If you notice, g has f of x as our input, and on the outside we have a natural log. So I'm just going to kind of say that's going to hint us into g of x is going to have some sort of natural log, and f of x is going to look something like something kind of that will get us to 6x minus 2. Now looking back over, we have f of g of x. We have g of x being inputted into f of x. Notice that natural log pops up again. I'm going to say, let's just use natural log of 2x as g of x. That would work, right? So if for that to be the case, that means that this whole thing is taking the place of x in f, which would mean that f of x would be 3x minus 1. Now checking just to make sure, we want g of f of x to be natural log of 6x minus 2, right? So that is going to look like natural log of 2 times 3x minus 1. And we know 2 times 3x is 6x, 2 times negative 1 is negative 2. If you look at that, those two are equivalent. So we're good. No further work required. Okay, so now for question 31, looking at for f of x is 1 over x, g of x is 1 over x plus 3. Find the new function in its domain using interval notation for the domain. Okay, so first, we're going to have f of g of x, which is going to look like 1 over x plus 3. Now, to get that 1 over x plus 3 on top, what we're going to have to do is multiply x plus 3 over x plus 3, which will give us just x plus 3. Because this one will cancel out with that, and all we're left with is x plus 3. So if we notice, our new function doesn't really have anywhere that the domain breaks, but our inside function g of x, because f composite g of x is the same as f of g of x. What we need to make sure is that this part does not break. So g of x is 1 over x plus 3. We cannot include negative 3 because we don't want to divide by 0. So our interval is going to look like all real numbers except for negative 3, which is going to look like negative infinity to negative 3, negative 3 unincluded, union, negative 3 onto positive infinity. So that is our answer for our first one. Because for our domain to work, it has to work with our new function, it has to work with the whole thing, it has to work with everything, our inner functions as well. So that's the main reason why. Now g of f of x, that's going to look like 1 over x plus 3, because that 1 over x is taking the place of that x. Now, I'm going to kind of rewrite this a little bit. Say 1 over x plus the 3, I'm going to write as 3x over x, just so I can get a common denominator so I can go ahead and add those across. Now this is going to look like 1 over 1 plus 3x over x Now here, since we have 1 over a fraction, that's just going to equal the reciprocal of our denominator. It's going to be x over 1 plus 3x. Now here, this function, sorry, let me rewrite that. This function is not going to work when 1 plus 3x is equal to 0, which means that x equals negative 1 over 3 is not in domain. Also, kind of like we did earlier, we need to make sure that any of our f of x values that we pass, or any value that we pass into f of x, are going to work. So 1 over x is f of x, which means that 0 is not in our domain either. So our domain is going to look like all real numbers except for negative 1/3 and 0. So kind of similar. I'm going to start with negative infinity up to negative 1 over 3. We're going to have a union. We go from negative 1 over 3 to 0, another union, and from 0 up to infinity. That's our new domain. Moving on, we have f of x plus g of x. That's just 1 over x plus 1 over x plus 3. I'm going to go ahead and add those together, just kind of create a common denominator. So this is going to be multiplied by x plus 3 over x plus 3. This is going to be multiplied by x over x. So we're going to end up with x plus 3 over x times x plus 3 plus x over x times x plus 3, which is going to give us 2x plus 3 over x times x plus 3. That is going to be our new function. Notice we have in our denominator, we have a polynomial down there, so we need to check when is that equal to 0. That occurs when x is equal to negative 3 or 0, so those are not in domain, just because, again, we cannot divide by 0. So our domain is going to look like all real numbers except for those points where it breaks at negative 3 and 0. So that's going to go from negative infinity to negative 3. We're going to have a union, negative 3 up to 0, union, then 0 up to infinity. Perfect. Okay, so moving on to question 32, we have let r of x equal 3x minus 4 over 2x plus 5. You want to find r inverse of y. So my first step, I'm just going to go ahead and rewrite this as y equals 3x minus 4 over 2x plus 5. You write that. So my first step is going to be to go ahead and just multiply this over out from under the denominator. So we have y times 2x plus 5 equals 3x minus 4. Now remember, our goal is to isolate this x and that x out from our fraction. So I'm going to go ahead and distribute this y to give us 2xy plus 5y equals 3x minus 4. And then I'll subtract our 3x and our 5y just to get our x terms together. So we'll have 2xy minus 3x is equal to negative 5y minus 4. Notice now all of our x terms are on the left-hand side. So what we can do is go ahead and factor that out, which leaves us with 2y minus 3 on the inside, that's going to be equal to negative 5y minus 4. Now just to get x on its own, you can divide by 2y minus 3. And that gives us x is equal to negative 5y minus 4 over 2y minus 3. Or our inverse of y is equal to negative 5y minus 4 over 2y minus 3. Perfect.